To be executed in 8051, it is often necessary to transfer program control to different locations. So this is very important. As a part of this presentation, we will go through some of these features like jump instructions, then call instruction, and some special feature that is associated with delay in case of microcontrollers. So as a part here, our objective is uh, definitely once you go through this, you will understand, or anybody that is a student will understand how exactly the jump instructions are helpful, how you can use them, what is exactly the syntax, then call instructions, role of call instructions, and execution, and then the delay estimation in case of 8051, because this is also very important part as far as the timer operations are considered, and even in case of communication, that is serial communication application, for baud rate calculation, a number of applications, other applications also, wherever the delay is very prime most parameter in case of real-time applications. So there also this particular calculation or estimation one should remember and one should apply as and when required. So one by one we will go through all these. So first thing is that looping. So as we know that in case of 8051, it is having various instructions under the category of arithmetic, logical, then branching, conditional, and so on. So wherever some sort of loop is to be formed, like something is to be repeatedly done, that is nothing but the looping, like calculation of factorial, or some sort of arrangement, or maybe in number of times something is to be in iterative manner is to be repeated. So in many such cases, or even from lookup table, some entries are to be taken, and in some interfacing applications, in a particular order the data is to be transferred, like that. So in number of, so repeating a sequence of instructions a certain number of times is something which is required. That is nothing but loop. Loop action is performed in general. The most general instruction is decrement jump if not equal to 0 the register contents. So here with the help of register it is carried out. You can see here the register is decremented, and if it is not 0 then it jumps to the target address referred by the label. Prior to the start of the loop, the register is loaded with the counter for the number of time repetitions, and the counter is going to monitor the entire mechanism. The counter can be loaded in anywhere as R0 to R7, any register, or a particular location, RAM location, or maybe simply any specific register also. So as a part of program, it is freedom that the programmer can take decision which particular register is used. Now say for example in this small set of instructions, uh, first instruction is move a comma hash 0, so meaning is that accumulator is made 0, so a is equal to 0. Then second instruction is written as move r2 comma hash 10, so load the counter r2 is equal to 10, so this is the counter loaded. Then add a comma hash 03, so meaning is that in accumulator contains add 03, so whatever is in accumulator that will get added with the number 3. So in the first step we have made a equal to 0, so now it will get added with 3. Now the accumulator contents are 3. Now next instruction is djnz r2 comma again, and again is labeled back to add instruction. What is the meaning? Repeat this same sequence, that is this addition of 3 in the accumulator contents. How many times? That how many times is decided by R2. So R2 is nothing but counter, and at present R2 is having 10. So meaning is 10 times the same operation is repeated. When R2 is going to become 0, then automatically DJNZ will result in contents of R2, since they are going to become 0, 0 flag is set, so it will come down, and the next instruction is move R5 comma A. So therefore whatever is in accumulator, that is now transferred in register R5. So this simple small code I have written. just to illustrate that there will be a similar kind of a repetition mechanism as a part of program. So there will be loop inside loop also. So jump is the thing, or that is a kind of a instruction which will help in such situation. So jump only if certain condition is met. So this kind of a operation may be like here it is ZZ, jump if so and so register is 0, like that. Syntax is ZZ label. So small routine just I have written, just see, move a comma R0. So accumulator is R0, ZZ some label I have given over somewhere, just shift the control, then move a comma R1. If a is equal to R1, then ZZ jump if a is equal to 0. So like that, anything like can be used only for register A, not any other register. This is like the condition ZZ, that is jump if 0, this particular instruction. Now second thing is just see, simple, determine if R5 contains the value 0. If so, put 55 in it. Something I have written. So move a comma R5. So copy R5 into A and now check the accumulator. So J and Z. So if A is not 0, jump if not 0. J and Z is jump if not 0. Move R5 comma hash 55. So not 0, then next, and if it is 0, then you have to copy 55 into R5 register. So basically conditional jumps from 8051 are based on the contents or the status of accumulator we are observing, and from the accumulator we are observing particular flag, that is say for example ZZ, then accumulator content we are observing, JC carry content flag status we are observing. So like that. Now n number of such options are available. So for 8051 there is one more, that is JNC. So jump if not carry. So if carry is equal to 0, then CPU starts to fetch the execute instruction from the address of the label, or if carry is equal to 1, it will not jump but it will execute the next instruction below JNC. Like see here, one small program, we want to add say numbers 79 F5 E2 and sum in register R0. Now here we are using simple operation, that is move a comma hash 0, accumulator is made first of all 0, move R5 comma A, meaning is that since A is 0, now because of that R5 is going to get copied by A contents, so that is 0, R5 is also 0, then add a comma hash 79. So accumulator contents are going to get added with 79, that is our first number. Then jump if not carry, some label I have given, say for example N1 here, so it will go there. If carry is equal to 0, add next number. If increment R5, so that is increment R5, add a comma next number, that is hash 0 F5. So in 79 F5 will get added. Again jump if not carry, increment R5 and add the third number. So like that simply we are adding. So just for illustration purpose I have written this particular. So anything, any application, wherever some such sort of jumping is expected from one particular address to another by means of say following some other set of instructions, or maybe to take some decision. So based on some condition, jump instructions are used. These are some of the most popular jump instructions which are used in 8051, like ZZ, jump if accumulator is equal to 0, JNZ, jump if accumulator is not equal to 0, DJNZ, decrement and jump if accumulator is not equal to 0 again. So this is special. Please remember, this is getting operated on the operand accumulator. It is observing only accumulator as a register, not R0 to R7, no other memory address, nothing doing. Then next is CJNE. This is again compare and jump if not equal to a comma byte. So jump if a is not equal to whatever byte you are used there for comparison purpose. CJNE, that is again compare jump if not equal to register contents with some immediate data, hash data. So jump if byte is not equal to data. Jump if byte is not equal to data. Then JC, jump if carry flag is set. JNC, jump if carry flag is 0. JB, jump if bit is equal to 1. JNB, jump if bit is equal to 0. JBC, jump if bit equal to 1 and clear bit. So simple operation. This all these instructions along with accumulator and some status of the flag, they are popularly used in case of 8051. So you remember them, and wherever needed you can apply. The address of the target must be within -128 to +127 bytes of the contents of program counter. Meaning is that all the jumps are 1 byte, like maximum length is, or distance in other words we can call, is of 1 byte only. So not more than that size bytes. The unconditional jump is a jump in which control is transferred unconditionally. So to the target location, there are two categories. So first one is called L jump, that is long jump. This is an unconditional long jump. It is 3 byte instruction in which the first byte is opcode and the second and third byte represent the 16-bit address of the target location. The 2-byte target address allows a jump to any memory location from 0000 to FFFF. So this is a 3-byte instruction and long jump, because the address is from range, that is the address range is 0000 to FFFF. In case of short jump, this is 2 byte. Okay, one more thing, as far as long jump is considered, though the program counter in 8051 is 16 bit, giving ROM address space of 64 kilobytes, not all 8051 family members have that much on chip program ROM. So this is to be remembered. The original 8051 had only 4 kilobytes of on chip ROM for program space. Consequently, every byte is very important. So for this reason, one more jump is made available under the category of 2-byte instruction, and that is short jump. So this can save the memory in many applications where space is short. So short jump is 2 byte. The first byte is opcode and the second byte is relative address of the target location. By default, since it is 2 byte, so relative address range space is only 1 byte space. So therefore it is from 00 to FF is divided into forward and backward jump, that is within the range of -128 to +127 bytes of memory. Relative to address of the current program counter, this jump is going to take place. If jump is forward, then the target address can be within space of 127 bytes and with respect to current PC. And if the target address is backward, then address can be within -128 bytes from the current PC. So this is something which is actually taken care. In addition to SJump, all conditional jumps such as JNC, JZ, DZ, and Z, they are also under the category short jump, due to the fact that they all are 2-byte instructions, and therefore the first byte is for opcode and the second byte is only carrying the relative address. The target address is relative to the value of the program counter. So this is very important. Now you can see to calculate the target address of short jump, you have to consider that particular address range. Like if it is more than -128 to 127 bytes from the address below the short jump instruction, then the assembler will generate an error stating the jump is out of range directly. For example, see here in the small code, my first instruction is org000 origin directive we have used, move r0 #0, that is r0 is loaded with 0, move a 55, so accumulator is loaded with 55, and now I have written zz jump with 0, where next. So next address is, and at that address the instruction is written as add a #77. Now see here, our program counter is at when ZZ instruction was executed. After that there is a next label. So the program counter is going to check, and it will go to the address 0009 if the condition is satisfied, that is accumulator is 0. And if not, so it will do in between increment R0, then increment A, increment A, that is accumulator will get incremented, and then again it will come to the same address. In the second part, when JNC is going to occur, so JNC will be, that is over. So how much it is, directly from the address is 000B, and over address it is 0012. So how much it is total, from JNC, that is from B to 12, it is going to jump. So jump if not carry, it is going to check, and that plus 05 will get added. So here you can see that is second byte, means the offset with which it is going to say jump. So that you can see in the that second part. Meanwhile there is move R0, comma A, R1 comma A, R2 comma A, R3 comma A, and at over once again add A comma R3, jump if not carry again. So it is going to go back directly to increment. So there is 0015. Here you can see FE is going to get added, and it will come back to 7. You can do the calculation. In F2 it will get added and it will come back. Here you can see in 0004. So there, after that there is second byte 660 of code, and then the relative address. So accordingly it is coming when it will get added with this 063, and it will come here. So this fashion actually it is working, and it can actually, when you proceed, and if we get a complete execution, stepwise execution, you can see in the simulator, step by step in that file all these addresses. So it is very clear, the jump and the respective set address. Call instruction is used to call subroutine. Now this is the next thing. Subroutines are often used to perform tasks that need to be performed frequently, no doubt. This makes a program more structured in addition to saving memory space. See, in case of jump, small number of instructions, maybe 1 or 2 instructions, 3 instructions, like that, they are to be repeated. If a complete set of some instructions, which can be used as a equivalent to function or kind of a subroutine, then you can go for call instruction. So long call is 3 byte instruction again. First byte is the opcode, second and third bytes are used for address of the target subroutine. Subroutine is located anywhere within 64 kilobyte address space. And A call is absolute call. So L call and A call, two are there. A call is 2 byte instruction. 11 bits are used for address within 2 kilobyte range. This is very, very specific as far as L call and A call is considered. Using instructions, you can again control the program counter. When the subroutine is called, control is transferred to that subroutine. Then the processor saves on the stack the address of the instruction immediately below lcall instruction, begins to fetch instructions from the new location. After finishing the execution of the subroutine, the instruction return transfers control back to the caller. Every subroutine needs return as the last instruction, because that is going to direct, or that is going to tell the controller or the processor where to go, and after return, it is going to understand that and it is going to proceed. The only difference between A call and L call is the target address for L call can be anywhere within 64 kilobytes address. The target address of A call must be within 2 kilobyte range, a small one. The use of A call instead of L call can save number of bytes of program ROM space, definitely. CPU is executing an instruction one by one, and that takes number of clock cycles, as we know that. So machine cycles of 8051 is an important issue. The CPU, whatever is taking these number of clock cycles for execution, that is nothing but the machine cycles. 8051 instructions and their machine cycles, normally you have to take into account to calculate time delay when any program is getting executed and particular subroutine is may be there, and if you want to know the delay, then you have to take into account that particular refer that particular list. In 8051 family, the length of the machine cycle depends on the frequency of crystal oscillator connected to 8051. This is very, very important. The crystal oscillator along with on-chip circuitry provides the clock source for 8051 CPU. The frequency of crystal connected to 8051 family is in the range 4 MHz to 30 MHz. Remember, for 8051 crystal frequency range is 4 MHz to 30 MHz depending on the chip rating and manufacturer. So these are chip specifications, manufacturer specifications, make, based on make it is going to get decided. Very often 11.0592 MHz crystal oscillator is used to make 8051 based systems compatible with serial port of the computer. So the original 8051 one machine cycle lasts for 12 oscillator periods. So one machine cycle corresponds to 12 oscillator periods. So it is not one to one, remember. So to calculate machine cycle for 8051, we have to take 1 upon 12 of the crystal frequency for the calculation purpose. So meaning is that, say for example, here period of machine cycle for 11.0592 MHz crystal frequency, how it will be? Actually, this one corresponds to 12. So if it is so, then how much it is? So you have to calculate it, whatever is your requirement. So therefore 11.059 divided by 12, that will give you the actual frequency, operating frequency. So that is 921.6 kilohertz. Machine cycle is, the duration is 1 upon 921.6 kilohertz is equal to 1 upon 0.85 microseconds. So remember, for 8051, for considering 12 megahertz frequency, actually it is 11.0592. To adjust the baud rate figure, we will talk about that also afterwards in serial communication related issues, baud rate calculation. At present, from delay point of view, remember that for 11.0592 as a frequency, that is a crystal frequency, then here the machine cycle period or machine cycle related frequency, that is nothing but the operating frequency, is 921.6 kilohertz. Same fashion, say for example, instruction wise if we calculate, then first instruction, it is move R3, 55. So one machine cycle. So there is 1 into 1.085 microsecond, period will be 1.085. Some small example I have taken here where number of instructions are taken into account. Second instruction is decrement R3, DEC R3. So this is also 1 byte. So 1 into 1.085, 1.085 microseconds. Third one is DJNZ R2, target. It is a 2 byte instruction. So 2 into 1.085, 2.17. Next is LJump. Again it is 2 byte, and SJump again it is 2 byte. Say for example, target address 1 byte target address we are considering. So 2 into T, 2 into same 2.17 microsecond, 2.17 microsecond. Then NOP, no operation. So that is 1 into 1.085. So 1.085 microseconds. And multiplication is a 4 byte. So 4 into 1.085. So approximately 4.34 microseconds. Now see here one more example. So here what we are asking is discussing is, find the size of the delay in following program if the crystal frequency is 11.0592. Okay. Now how will you do that? Say for example, one small code I have taken just for the sake of calculation I want to show. So move A, 55H, move P1 comma A. So accumulator contents transfer to port 1. A call delay, complement accumulator, and S jump again. So as if it is 1010 flickering we are doing. Okay, because CPL I have written, so as a complementing S jump. For the time delay, we want to put there so as to get a kind of say effect. Delay routine move R3 comma 200 I have taken, and DZNZ R3 comma here, so remain in the loop until it becomes 0 and return. Simple way to short jump to itself in order to keep the microcontroller busy is here. We are engaging it, so instead of here also we can use $sign also, and machine cycles for this delay will be move R3 comma 200, that is 1, DZNZ 2 byte, and return 2 byte. So total 5, 200 into 2 is internally, and plus 1 plus 2, so multiplied by 1 into 0.85. So resultant will be 436 point approximately 255. So this is one small example I have taken so that you can see here, time delay we have calculated. R3 register can take 255 maximum, not more than that. So therefore simple ones, some small count I have taken, and it is going to repeat. The total delay will be of approximately 436.255 microseconds, so that the blinking will be visible, and like that. General size of the delay, the following, the crystal frequency is R3 is 250. So here you can see now the loop is here NOP, 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 NOP. 4 times I have added so as to increase the delay. So again 1 byte. So total, because based on that the repetitions will be. So 250 times, no doubt, but multiplied by how many? In one iteration, how many it is going to take? 1 byte of move, again NOP, 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 NOP. So total 4 times, and plus DZNZ 2 bytes, so that is 2. So total multiplied by 250. So that will be the delay 1627.5 microseconds. See here, this 1 plus 1 plus 1 plus 1 plus 2. Why it is coming? Because the loop is going to get executed how many times? 250 times. But 250 into 1 it will not be. Why? Because inside loop whatever is going to happen as a part of loop. So total how many bytes the processor is going to consider? 4 plus 2, 6 bytes. So therefore it will get multiplied by 250, and that will get multiplied by the period taken for one particular byte as a machine cycle. That is one machine cycle. Okay. So machine cycle count in terms of time, it is becoming 1627.5 microseconds. The 2 instructions outside loop, we get it like NOP, NOP. If we add, then definitely it will get 3 into 1 into 2 into whatever number of bytes you are going to add, that is one particular byte correspondingly, that one machine cycle it will get automatically added. So this way you can do that, repeat number of times. In general, there are 2 factors that can affect the accuracy of the delay. One is crystal frequency. The duration of the clock period of the machine cycle is function of the crystal frequency. So definitely it is very important. The original machine cycle duration was set at 12 clocks. Advances in both IC technology and CPU design in recent years have made 1 clock machine cycle a common feature. In case Atmel's 89C51, which we are taking as a reference controller for entire our practical sessions, so it is 12 clocks per machine cycle 12. P89C54X2 Philips 6 machine cycles. DS 5000 Dallas Semi, so it is make 4 machine cycles, and DS89C 420, 30, 40, 50 this series. So it is taking only one machine cycle. So this is the kind of a advancement you can see. For example, for various devices, if we calculate from various manufacturers, like clock crystal frequency is 11.059, then for Atmel 89C51 it is becoming 11.59 592 megahertz divided by 12, 921.6 kilowatts, and therefore period is 1 upon 921.6 kilowatts gives 1.085 microseconds, or that is nothing but 1085 nanoseconds. In case of P89C54X2, so since there are 6 cycles, so therefore divide by 6, it gives 1.8432 megahertz, and the period is 1 upon 1.8432 megahertz gives 0.5425 microseconds, that is 542 nanoseconds. In the third case, DS5000, so it is divided by 4, because in earlier table we mentioned how many cycles it takes, 4 cycles, so therefore 2.764, and then period is 1 upon 2.764 megahertz gives 0.36 microseconds. And the last one is, for example, DS89C 4X0 series, so that gives one machine cycle only, 11 points crystal frequency divided by 1, so that gives as it is, and therefore its period is 1 upon 11.0592 megahertz gives you 0.0904 microseconds, so that is 90 nanoseconds approximately. So this is just one sample. In many other applications at the time of actual programming, uh, especially in timers, we will once again comment on the delay, and even in the applications wherever delay plays important role for like the effect we want, that is it is on off effect of any other. So at that time also in keyboard interfacing or anywhere, so you have to take into account this type of a calculation, you have to estimate it, and then only you can proceed. So to summarize, in this whole session, we have discussed in the beginning about jump instruction. So there are mainly jump instructions associated with accumulator conditions and flag condition. So to summarize, we have seen there are number of jump instructions like JZ if accumulator is 0, JNZ if accumulator is not equal to 0, DJNZ decrement and jump if register contents are 0, CJNE compare and jump if not equal to a comma data, that is accumulator not equal to data, and CJNE register comma hash data, that is immediate data, register content with immediate data, compare if not equal to, then also you can jump. Then JC carry flag is 1, JNC carry flag is 0, JB jump if bit equal to 1, and JNB jump if bit is equal to 0, and JBC jump if bit equal to 1, and moreover this is additional, very important, that is jump and then clear the respective bit. So this is also very useful. So jump instructions as conditional instructions, they are having very significant role in the program. After that we discussed about call. So there is a call and L call. So long call, long subroutine call 3 byte, and a call, absolute call, that is 2 byte. So this is whenever you want to get the things done faster, so you can go there. Even we have seen L jump and S jump, that is LJMP and SJMP. So long jump again 3 byte, target address is to be relatively 16 bits, and a short jump target address is relatively 8 bits. So oscillator period wise, all these A call, L call, return, return from interrupt, age, absolute jump, long jump, short jump, these are all 24 oscillator periods they all are taking. And even jump instructions from JC, JNC, JB, JNB, JBC, so they are all also taking 24 clock periods, oscillator periods. So this is all about. In coming session, definitely while writing programs, we will use all these basic concepts associated with call, jump and delay associated with 8051. Thank you.